the previous lectures, we have seen the details of the differences between the turning centers and the milling center. What we are going to now see is how to write the programs. And notice here the procedure is going to be very similar to the one that we are using for the machining centers. So I may be going a little faster, so see the differences. Now the reference point, that is the machine datum, is a fixed position as in the case of milling machine, but program origin is the datum position that you are going to fix on the part, like the way that we have done for that of the machining center. And then machining origin is essentially the point about which the turret indexes. So these are slightly different from that of the machining center. Now if you can see here, we have the part blank here. So the part origin is fixed, so you will have the positive Z and positive X. Then you have machining origin, which is about the center point about which the turret indexes, and therefore when you have the tools, the tool offsets are essentially the length of the tool from the center of the tool offset point. So in terms of tool length along the x-axis, tool offset along the x-axis, and tool offset along the z-axis. So z offset and x offset will be loaded for each one of the tools. Okay, this is what it is. So you have the x offset and you have the z offset for each of the tool, which will have to be positioned. So this will be the tool datum, and which is the one which we are going to use. So you have the check, so the part, then you will have the axis system for the part. So you have the axis system for the tool and the way that you are going to do. Now when the machine is on, the tool will consider as if the offset point, that is the origin of the tool, is going to be at the machine home position. So later on you will have to move that to wherever that you want, because we are not going to make use of the machine home position, but we are going to fix these two with reference to each other based on the programmer convenience. Okay. Now the setup procedure that is going to be done in the case of lathe is load the required tools, load the part blank, and when you are loading the part blank, make sure that work overhang should not be long, and then tool offset values are measured and loaded. Now tool offsets means we will have to specify the x and z axis tool offsets, like the one that I have shown a little earlier, and then tool nose radius value and the tool nose orientation number. Again, I'll talk about that slightly later. Now tool offset register values will be loaded something like this. You have offset register number 1, 2, 3, etc. whatever number of the ones that you have. You have x offset value, z offset value, tool nose radius, and tool nose radius direction. So these values depends upon the units that you are going to use, and I am showing here as metric values. Now feed specification is similar to that of the machining center, so F value, and either you can specify using millimeter per revolution or millimeter per minute. Whenever you use millimeter per minute, you will have to give G98, and if you want to give it as millimeter per revolution, you will have to give G99. That's the only additional G code that will have to be given. And speed, again similar, either you can give direct RPM and constant surface speed, that is meters per minute or feet per minute. Again we will have to use G96 and G97 for the constant surface speed option. Constant surface speed is important in turning because the work is rotating, and whenever work diameter changes, if you don't have a constant surface speed option, if you have a constant RPM, what will happen is when the diameter changes, this actual cutting speed changes. For example, if you are doing a taper turning operation, from the small diameter to the large diameter, when it is changing, your tool cutting speed is going to change. Now since the surface finish is proportional to the cutting speed, what will happen is at the small diameter end you will get rough surface, whereas the finishing side you will get the surface finish. Same thing happens in facing. When in the larger end the finish will be good, but as you go towards the center, it will become really rough. So whereas if you use a constant surface speed option, what happens is controller will continuously change the RPM such that the cutting speed remains constant throughout the diameter range. This is normally achieved by using a G code. We will have to use G96 for constant surface speed option. But default mode is G97, that is RPM. So if you want to have the constant surface speed option, you will have to give G96 in place of G97. Also, when you give constant surface speed option, what can happen is when the diameter becomes extremely small, the RPM may become infinite. Infinite means it's not really infinite, but whatever is the maximum surface RPM that is possible on the machine. Either you can use that maximum limit or you can limit the RPM. For example, sometimes if you are using a check may have a limiting RPM. Though your machine is capable of going up to 5000 RPM, if your check has only capability to go up to 3000 RPM, if you try to run it at more than 3000 RPM, the check jaws may come off and the workpiece may become loose and fall off the check. So we have to limit that speed. That can be done by using the G50 code. So whenever you are using constant surface speed option, it is a good habit to put G90 and specify whatever is going to be maximum limit. In this example that is shown here, we are saying G50 S4000 and we are saying maximum spindle speed RPM should be maintained at 4000 RPM, and then you say G96, that is constant surface speed option, and say S200, that is spindle speed is set at 200 meters per minute. And later on in the program you can change it to constant RPM by simply saying G97 and S2, whatever speed that you require. Now T, same as the machining center, so we will say 2 digits specify the turret station and the last 2 digits will be specifying the tool offset. So for example, if we want to change from here to here, all we will have to say is, because currently tool number 1 is on, we want to bring tool number 4, so we say T04, so that the new tool will come into position. The way the offsets are going to be measured is, you normally put a part blank of known diameter and length and set the job inside the check and set the first tool to come into operation and bring it and touch it to the surface, so that when it is touching this surface, here you are making it as the z-axis 0, and similarly when you bring this and touch it at this point, you will be making the x-axis. It's not 0, but whatever is going to be the radius of the part blank. So you will put it and then you will be able to measure whatever is going to be the offset value. Okay, program number, generally word address is used. Again, this is similar to the way that we use. Block number is same, no change in operation, it will be same as machining center. Coordinates, normally XZ are used. Only difference here in turning centers is that for the purpose of specifying absolute and incremental coordinates, we make use of different word addresses. XZ are used for absolute coordinates and UW are going to be used. U will be incremental X and W will be incremental Z. That's what is there. Then the miscellaneous functions that are used are again similar. M00 program stop, M01 optional stop, M02 end of program, M03 spindle start in the clockwise direction, M05 is spindle stop, M08 is coolant on, and M09 coolant off. So these are same as the way that we are using in the milling machines or machining center programming. So there is no difference in terms of the miscellaneous codes. M13, M14 are the same. Similarly M30. So codes remain more or less the same. Now preparatory functions are also the same as we use in most of them. Motion commands, M000 we are going to use it for rapid positioning, G01 we will be using it for linear interpolation, and G02 is used for circular interpolation clockwise, and G03 is circular interpolation, counterclockwise direction. Now these are all the same as that is used. Only thing is that you can see examples slightly. So for example, you are here, let us say at 50, 20, that is the start point, and you want to go to B 15 point, so rapid, and then you want to go like this, rapid movement from A to B. Okay, so A is 50, 20, so we say in absolute mode N040, Z00, X 15.0, Z 2.0. This is exactly like the way that you have done. And if I want to do in the incremental mode, so we are at this point, that is 50, 20. From 50, 20 we want to come to 15, 2. So 50 minus 15, so 35. Because we are going in the negative x direction, we say U for incremental x minus 35, and W, that is incremental z, it is minus 18. That's what is specified here. So you can have either absolute or incremental mode. Actually, since we are not using G90 or 91, it's even possible to have a mixed mode. That means one coordinate can be specified in absolute, one coordinate can be specified in incremental. Like for example, here N40, Z00, U minus 35, that is x incremental, and we are giving Z absolute. So it is possible for you to mix the way, whatever way that is convenient to you. Or we can also have x in absolute and Z in incremental. Both are possible. So you can go to any way that you require. Now linear interpolation is also very similar, because we will be giving G01 is the linear interpolation. So for example, we are coming at this point, let us say we are going to the start point and then go like this and come back. So this is rapid motion, this is linear motion for the purpose of turning, and then rapid motion for the purpose of retracting. Okay, so starting with 50, 20, going up to 15, 0 rapid, and then go to 15 minus 35 in feed mode, and then from there go to 30 minus 33 in the rapid mode for the purpose. That is how a typical turning cut is taken. Okay, programming from A, B, C, T. We are assuming it to be radius programming. So in absolute mode, what we are going to have, Z00, X 15, Z2, so that is this coordinate, and then we go from there Z01, so we will specify X and Z, that is the endpoint of this, and also make sure you are specifying the feed rate because it is G01, and then from there you come back because it is rapid, so we will say G00, then we say whatever is going to be the coordinate. So you notice that the programming is almost identical to that of the machining center. In fact, at this point of time we are not really worried about the nose radius directions. So later on we will see how to take care of that into account. Now if you have to do the same programming in incremental mode, again what we are going to do is, U will be, so it's Z00, U minus 35, W, so U will be incremental, so it will be this minus this, because the actual distance moved, that is what is specified here. U along the negative direction, W along the negative direction, so it is negative, negative. Then from there G01, U, because your X is not changing, so therefore U0, you don't even have to give this U0, you can omit that. Then W minus 37, so whatever that, and then the feed rate, and again you can do that. So you can use either absolute or incremental programming the way that you want. So G01, if you want to have change the sequence, mixed mode also you can do. So you can use absolute, incremental or mixed mode. The only reason why we want to use any one of them is we would like to make use of whatever dimensions that are given in the part drawing directly without doing any additions. That is the most important point to remember. Okay, let's come to the circular interpolation. In the case of circular interpolation, clockwise and counterclockwise, like the way that we use. So here let us see an example. The tool is starting from here. going rapid to this point and then going along a linear interpolation to make this, and then doing a circular interpolation, and then going rapid back to this. Okay, rapid positioning, linear interpolation, circular interpolation, then going back in linear. So programming from A to B, B to C, C to D, D to E. A to B is rapid, B to C is linear interpolation, C to D is circular interpolation, and then D to E is rapid. Okay, so using an absolute mode, what we have is G00, that is the rapid, A to B, X12, Z2 at this point. Then from there linear interpolation, so G01, X12.0, Z minus 20, F120, and then circular interpolation, we use G02 along the circular clockwise direction because it is moving like this. Then X22.0, Z minus 30.0, and radius of 10.0, F100. Feed rate has to be specified. If I don't specify this feed rate, it will take the same feed rate that is present in the previous. So normally when it is taking a circular interpolation, it is a good habit to reduce the feed rate. Then after the circular interpolation is completed, we will retract the tool to go to the starting point. You can do the same thing in, only thing is that slight change that has been done is, instead of specifying the circular interpolation in radius format, you can also use the I and j that we have used, that is the center point coordinates. Whichever is convenient you can use. Then you can use G0 for dwell like the way that we have done. Normally it is specifies the programmed pause in the axis. Now like G0 for x 4.5, that means it will be a dwell of 4.5 seconds. Normally very few times we would like to use dwell. Okay, the main thing that to remember in the turning center programming is cut planning. What happens is, because we will be starting with a raw stock, which is generally bar stock, and we will be removing a large amount of material before the final contour is achieved. Okay, so therefore what we will be doing is, we will have to identify how many cuts are to be given and how and where. Okay, so to do that, it is necessary to plan all the roughing cuts and then identify the coordinates through which the tool will have to move in order to achieve those cuts. For example, let us see here, we have, this is the part that I have, and we want to make a rough cut. Now this is the maximum amount of depth of cut that I can take with the tool. Okay, so what I will be doing is, I will be taking a number of rough cuts, this 1, 2, 3, 4, 5, 6 rough cuts, in order to remove bulk of the material, and with the leftover material I will take a finish cut, so that I will be getting a smooth surface that is required. Now this is simple if I have, let us say, a rectangular cut, but very often you may have a slightly different, that is, you have a tapered cut. Again you will have to do the same. So we will be taking 1, 2, 3, 4, 5, 6 cuts to remove the, and then what I will like to do is, because there is a large chunk of material is left out here as shown here, so I may take a semi-finish cut here and then take a final finish cut here. So normally whenever you have arcs and inclined lines that are present, it is a good habit to make roughing cuts and then a semi-finish cut and follow that with a finish cut. Now again you will have to identify all the points through which it is that will be going. So you need a large amount of coordinate calculation in terms of cut planning. So again I suggest that whenever you are doing the cut planning, make use of any CAD program that you are familiar with or accessible, so that calculation of the coordinates become much more easier than doing the. Now I am showing you an example here for the purpose of calculation. Let us say you have a component shown here with a 1045 steel to make a part program using the CNC turning center. So let's say you have this part. What you have is, you have a chamfer here, you have a chamfer, then a turning, and then an inclined surface and a face, and then followed by a chamfer. So you are starting with a 40 millimeter diameter raw stock and then finally bringing that to 20 millimeters. So for example, from here to here it is a total of 10 millimeters. Again, since the 10 millimeter cannot be removed in one cut, we will have to break the 10 millimeter into 4 or 5 cuts depending upon the maximum depth of cut that you can take for the chosen cutting tool that you have. So what we do is, for example, initially I may like to take a maximum depth of cut of 2 millimeters is that is, say I planned. So I will take one cut here, next 18, then I may go to 15, and I may go 1, 2, 3, 4, 5 cuts are taken. So what I will do is, I will write the program, metric units. I don't have to say G90 or 91 because I can use the XG and UW. So go to the initial start point, okay, and then Z65, that is the starting point, and then tool change, whatever tool that I want to have, and then start the tool, specify the RPM that I want to, okay, then because the coordinates are calculated here, so I will use those coordinates for the writing the program. Position, go to the depth, so I go to the 8, go up to this point and then retract, go to the start point, and then, so it's simply going through those steps, and every time I go through, give one more step, and then stop the spindle and end of the program. So all I am going to do is simply locate the coordinates. So all I have to do is, I will have to locate the coordinates correctly. That is the most important part in cut planning. So what the best thing to do is, try to create a drawing in AutoCAD and then offset it and find out what are the exact coordinates through which it will have to move. So if you do the simulation, that's what will come out. Now let us go a little more detail with only finishing pass is obtained. Let us say I am not doing the roughing operation, but only the finishing operation here. Okay. So what I have is, I will have the circular interpolation here, straight line interpolation, straight line interpolation. So I will have the tool somewhere here, bring it to this point, then go like this, and then come back and then go to the start point. That is the sequence of motions that we are going to have. Start, G21 is assuming you are using a GE Fanuc as the metric units. Okay, go to the initial position, go to the start point, because here from the X, because normally we come to the X start position and then to the Z start position. Okay, then get the tool that is required, tool number 1, start the spindle and go, and then bring the tool to a point which is X 2.5 and Z 2 point. So we come to a point which is very close to this, and then touch the surface. So that's why from here we are touching G1, so, and then specify the feed rate. So the tool will actually be touching at this point, and then from there you move the tool along in this direction, X5, Z minus 5 for this. Then from there, from X5 you go to Z minus 17.5, because the same X is there, but along the Z direction you are going. Notice the Z values are all specified negative because your datum is located at the end point. Always we will be using the Z datum as the end point of the workpiece, so that all Z negatives will be taking the tool inside the workpiece. Then here it will be counterclockwise direction motion, Z03 x10 minus 22.5 here with a radius of 5, and then we take Z1 for the purpose of going up to minus 22.5. So it will come to this point, and from there we will retract and then stop the spindle. So what we are going to do is think of x and z motions going along the path. Now one assumption that I have made at this point is I ignored the tool nose radius. I am assuming that tool nose radius is 0. But in real practice, tool nose radius is going to be a finite value, and then you will have to offset the tool path by an amount equal to the tool nose radius. But since tool nose radius is equal to 0.8, which is very small value, we can ignore for the purpose of practice. But if you are going to really machining, you have to take that into account. Otherwise, all the dimensions that you are going to get will be wrong. So the simulation will actually provide you with this. Now there are some earlier controls, particularly Fanuc, have provided special codes for generating the chamfers and the corner radius. So whenever you have a 45 degree chamfer or a 90 degree corner radius, they have made it easier by doing. But actually this has been continued in the current controllers, but only available in old controllers. So let us not go through it, but it is possible to, if you have old controls, it will be possible to do them much more easily. Another important part that you will be doing is grooving operation. Grooving, you will have to use a special tool, that is a grooving tool or a parting tool. Okay, normally grooving tool will have a certain width, and what you will be doing is, because grooving is where the tool will be ending up inside the work material, what is important is when the tool goes into the depth, you will have to stop the tool for a while. That means you will have to give a dwell at the end. So we will say position the grooving tool at a clearance plane position, then go to the depth whatever that is required. Okay, using Z01, go to the depth using whatever feed rate that is required, and when you reach that point, give a dwell and then come back. So position the tool, go to the depth, stop there for a while, and then come back to the starting point. Now here of course I am assuming that the width of the groove is same as the width of the tool. But if the width of the groove is larger than the width of the tool, you may have to traverse. So what you will be doing then will be, take the tool, go to the depth, come back, then move the tool side, then go in and come back till the width of the groove is equal to the width as given in the job. Okay, now let me go through a complete example of a part where we will be processing all the operations. That is, we will be doing the roughing operations as well as the finishing operations. As I said, first step is to do the machining plan. Okay, so now this is the contour that I want to have. Okay, this is the contour that I want to have, and so I know what is going to be maximum depth of cut. So I will draw horizontal lines that are parallel to the z-axis. So I will make the parallel lines to the z-axis till it interacts with the offset contour here. And then what I am going to do is get the coordinates of all of it, all these points. What I am going to get is get all the coordinates of these points. In fact, either you can do this manually, that means on a drawing board you can make this, or if you have access to CAD, you probably will be better off by using the CAD for the purpose of offsetting. So you get the coordinates of these, both the z and x coordinates. Okay, so now what you get is these are all the roughing coordinates. what you notice here is this is one roughing cut, second roughing cut, third, fourth, then fifth roughing cut, sixth roughing cut, 7, 8, 9 roughing cuts. So you require 9 roughing cuts to remove the bulk of the material. And when those roughing cuts are removed, then you are left with this material. Okay, that material will be removed in the semi-finishing cut, and then you will be left with the finishing cut. So you require 7 roughing cuts, 1 semi-finishing cut, and finally 1 finish cut. Okay, so roughing program therefore will be, again, the starting blocks are same like all the programs. Okay, so these are all the starting blocks. So we will start moving along. So I have all these coordinate values. What I am going to simply do is bring the tool to this point, go up to this, go back, go to the start point, go to the next cut, go up to this, come back. That is what I am going to program. Okay, so first take the first depth of cut, so go up to this and then go to the depth that is required and then retract a little bit and then go to the start point and then take the next cut, go to the depth and then retract, go to the start point, then take the next cut. So that is how you are going to complete all the 7 depths of cut, 7 roughing cuts. Now all these coordinates are obtained from the, and notice when I wrote this program, somewhere I am using the absolute coordinates and somewhere I am using the incremental coordinates. So depends upon the convenience in avoiding some calculations. So that completes all my roughing cuts. So that is the last depth of cut. So that completes. So when I remove all the depths of cut, that is the roughing cuts, what you notice is the material that is left out here. So you can notice this is the left out material. Now I don't want to take a finish cut, one single finish cut, because this is too large a material variation, and if I try to remove all of this in one cut, the tool is going to experience vibration, so it is not desirable. So I will again get all the coordinates for these points and create a, this is the simulation of the program with those roughing cuts. Okay, now the finish cuts will be, leftover material will then be cleaned by a semi-finish cut followed by a finishing cut, 2 cuts. So I will have 1 semi-finish cut going through this and 1 finish cut, so that your surface finish of the job is going to be really good. So finish program, change the tool if you want to change. Then what you will be doing is spindle on, specify whatever is the speed that you want to, then semi-finish cut. So you just simply go through all these coordinates. And then again with the same tool you can attempt the finish cut. And once it is done, you retract to the safe position and stop the spindle and then end of the program. So when you simulate the semi-finish, that's what the shape that you should be able to get. Okay, so what we have seen so far is that the programming for turning centers is very similar to the machining centers, and the way that we are going to do is we will be creating the cut planning. That is the most important part after the process planning. So prepare the cut planning, make use of either a normal drawing board or make use of a CAD for the purpose of getting the coordinates where the tool will be moving in order to get the cuts, roughing cuts. Then take a roughing cuts, follow it with the semi-finishing cut, and finally the finish cut. So get the coordinates from the CAD and translate them into the programming. Now in the examples that I showed so far, I haven't really taken into account the tool nose radius. But if we want to take the tool nose radius into account, what is to be done? Because without tool nose radius, we are assuming the tool tip is touching the workpiece surface. But if it is not, what we will have to do is, we have to offset the tool path by an amount equal to the tool nose radius. Okay, that is all that will have to be done. So all I am going to do is offset this tool path by an amount equal to the tool nose radius and calculate those coordinates like this, and then use that data for the purpose of programming. So if I want to take tool nose radius account that, now this is a little more complicated because of that effort involved in offsetting the tool path. But again, the procedure is very similar to the one that you have used for machining center, no difference. Also, we can use the G40, 41, 42 like we have used there and specify the tool nose radius value in the offset value. So that way also it would be possible. Tool nose radius compensation. Tool offset file shown with the separate column for tool nose radius direction. And when the tool nose radius compensation is to be specified, it is necessary to specify the correct directions, because that's the only point to remember. These are the some of the directions, the way the compensation will be provided. I don't think we would like to go into the details of this at this stage, but yeah, it is important. Okay, one more point before we close to see is thread cutting, because that's an important aspect of any turning center programming. Now, whenever you are doing the thread cutting operation, two things will have to be noticed. Whatever is going to be the depth of cut to be taken, and what is the thread form, that is the actual shape of the thread. Now there are standards available like the ISO standards, so that will tell you exactly how to calculate the maximum depth, etc. So that will be known. And also thread cutting can be considered simply as a turning operation, except that the feed rate that is to be chosen will have to be same as the lead of the thread that you are going to cut. That's the only important point to remember. And shape of the tool that you are going to use is not different from the shape of the thread you have. For example, if you are going to use an isometric thread which is a 60-degree angle, so the tool shape will have to be a V shape with 60 degrees. That's what you will have to have. So this is an example thread cutting tool that is shown here. So this is for internal thread cutting and this is for external thread cutting. So you will have exactly the same ISO thread form. Okay, now the other point to remember is depth of cut can be specified. There are two ways of giving the thread of depth of cut. So let us say this is the shape of the thread to be cut, and because it will have to have the same shape, the tool. Now tool can go into the thread directly, that is perpendicular. Sometimes we call it as plunge feeding. When you do this, what happens is the tool will be cutting on both the flanks, left flank as well as the right flank. And because of the reason two sides you are cutting, the rake angle has to be maintained as 0. And when you maintain the rake angle as 0, because of the two sides cutting, it is going to be relatively inefficient cutting, and because of which you will experience vibrations. So therefore it's not desirable. But however, calculations are easier with plunge feeding. Other way to do is what is called as compound feeding, wherein the tool will be moved along the flank of the thread, so that only one side will be cutting. This will be only clearance will be there on this side. So it will be cutting only on this side, so you can maintain a positive rake angle here. Okay, so the back rake on the tool can be made as positive. That's what makes the compound feeding a better alternative. But only thing is, because compound feeding is moving along the thread, we will have to take the thread angle into calculation when you want to program the next point. So that will be a little additional calculations that are to be used in the case of compound feeding. That's why sometimes people will prefer to use plunge feeding unless the surface finish becomes an important element. Yeah, plunge cutting thread takes place along both the flanks. Therefore, this would mean that cutting tool would have to be provided with a 0 or a negative rake angle. In addition, the relief along the cutting edges cannot be provided. So that results in poor surface finish and lower tool drive, and generally it is not preferred. Okay, this when it is going along, this will help in more smooth flow of chips, and therefore generally this is a much preferred form of feeding. Because as I said, thread cutting is identical to normal turning operation. The only thing important to notice is we have to use a special code called G33 for thread cutting, so that it will take care of thread chasing part. And if you are familiar with thread cutting on a conventional lathe, we will be using a chasing dial to follow. That means you will always start the thread, cutting the thread at the same point. So that will be achieved by using the G33 operation. Let us take an example here. Suppose if I want to cut a thread, normally what we will do is I will bring the tool to this point, take the depth of cut, and then cut the thread, retract and come to the starting point, and then take one more cut and do like that. Okay. So now let us say this is an M20 2.5, that means it has a lead of 2.5 millimeters with a outside diameter of 20. Now let us say, for the sake of convenience, I am doing a plunge feed, and I will take a depth of cut of because I have to remove a total of 1 millimeter. So it will be, I will remove first step 0.6 millimeters, next step 0.4 millimeters, next step it is 0.4, 0.2, 0.1, 0.06, gradually decreasing, because if you notice in the plunge cut, as you go along, the contact length is increasing between the tool and the workpiece. That means the area of cross section of the chip is increasing as the tool goes inside. That is the reason why we want to start with a large depth of cut and gradually decrease the depth of cuts as you go along till we achieve the final finish cut. Okay, so we'll say start with set the spindle speed, whatever that is required. Okay, generally we set the spindle speed lower spindle speed because the feed rates are going to be very high. So get this thread cutting tool, position the thread for the first cut, so bring to this point. Okay, then you say G33 because you need this for thread chasing, that is the starting point of thread will always be at the same point where you will be cutting, so that you will be following the same thread. So complete the first cut, so you will go from here, go all the way to this, then retract, go to the start point, then next take the depth of cut, and then say G33. Now G33 is non-model, unlike the other G codes. G33 is non-model, so that G33 will be operational only in the block where it is programmed. So we will be giving it every time when it is required. So G33, it goes to the end point, then retract, go to the start point, then take the next depth of cut. So similarly we take all the other cuts, and then finally you take the last finishing cut, go through it, again give G33. So that way what you notice is the programming will be very similar. For it's almost looks like turning, it's no different. The only difference is we will have to add the G33. Now when we have seen this, what you can have is that the length of the program is a lot, because we have large number of multiple cuts are to be given. Again, the way that we have used CAN cycles in milling, we can also use CAN cycles in turning. The advantage is when you use CAN cycles, bulk of the programming can be eliminated, and that makes life easier, and also you can easily follow the program. Now for example, you can have a rough turning cycle. Let us say I have to take 3 rough cuts. What I am normally going to do is start point, go to the depth, do the turning, retract, come to the start point. So this will be rapid, feed, feed, rapid, and I will have to do the same. So what I am going to do is the rough turning cycle with these 1, 2, 3, 4, these will be embedded into one cycle. Move rapid to the x coordinate specified to take the depth of cut. Move at feed rate, cutting the metal to the z coordinate specified. Retract at feed rate and then retract to the start point. Okay. Let us say we have a depth of cut of 2.5 millimeters and we will start with 1.5 millimeter above. So what I am going to do is when I give a can cycle, I will say this position at the start point and then I specify whatever feed rate that is required and we say first rectangle cut. So this is G90 is the can cycle. So G90 x 19 z.2. So this is equivalent to 4 blocks. Okay, next cut and next cut. So if I am not using the can cycle, these 3 blocks would have been given as 3 into 4, 12 blocks. That's what makes it easier. So instead of writing 12 blocks, I can write only 4 blocks of information. That's what has been done here. Now you can have similar can cycles for, because this can cycle can be used for writing taper also. Also we can have the same can cycle could be used for boring. So you can use the same can cycle for boring, turning and taper turning. And you have a similar can cycle that is available for facing, taper facing. Also you have another can cycle that is available for thread cutting. So by proper application of these can cycles, it is possible to write programs very similar to the milling machine programs. Okay, thank you.